Hey guys, welcome back to another video. Today we're going to be looking at the atomic structure and the periodic table topic in chemistry. We're just going to look at the very first part today about atomic structure. So we're going to start up here with atoms and we're going to work our way around to all about equations. So let's get started. So atoms are the kind of building blocks of everything. They're the smallest parts really, and there are parts that subatomic particles and subatomic particles that make up atoms, but it's very hard to get them to exist on their own. So for the most part we consider atoms to be the smallest parts, and they were originally proposed as that in ancient times. So atoms actually consist of two parts with three different types of subatomic particles. You've got the nucleus and you've got the shells. And the nucleus contains protons which have a positive charge and neutrons which have an overall charge of 0. Now this is important in further topics, particularly when you're studying radiation in physics, and a lot of other stuff, particularly to do with isotopes and other things like that. But it's important to note the charges of these. So the electrons, however, are not part of the nucleus. So the nucleus is in the middle of the atom, and I'll be looking at the different ways that an atom has been structured in another video. But the centre of the atom is the nucleus, and there are shells around it. So it kind of looks like what I'm just going to draw in the top right corner here. So you've got your nucleus here, where it's coloured in red, and then you've got electrons around the outside, like so. So this is the most up-to-date and accurate model of an atom that we have. Obviously, I bet someone else could draw it better than me, but that's our the current model that we have. So in the middle you've got the nucleus with the protons and the neutrons, and outside these little crosses represent electrons. And the electrons have a negative charge, and while protons and neutrons have a mass, which we'll get onto in a minute, electrons have almost no mass. So it means that when you're calculating stuff that we will do in a short while, it means that you can ignore all the electrons. You'd have to have a lot of electrons to even amount to one mass in terms of what we're looking at later. So you can negate any electrons in the mass. So atoms are very small, and they don't have a lot of mass individually, and there are bigger and smaller atoms. But generally, atoms will be around 0.1 nanometers. Like so, which is 1 × 10⁻⁻10 meters. I'll be doing a topic on standard form some other time in the future, so if you need help with that, then I guess you're going to have to wait, but keep an eye out for that. Now, it's important to note that the amount of protons in an atom is equal to the amount of electrons in the atom. Now, it's important to note that I'm saying atom here, because later on when you are introduced to ions, the number of electrons is not equal to that of protons. But in an atom, the protons and electrons have equal numbers. And the protons contributes to your atomic number. So if you notice here, this means sodium, and sodium has an atomic number of 11, so it has 11 protons, and an atomic mass of 23. Now this means that it's got 11 protons, 11 electrons, and you take 11 from 23 to get the amount of neutrons, which is 12. So moving on to our next point, because I've covered everything on that one, we've got elements. So elements are atoms with the same atomic number, so the same amount of protons, and this is because protons decide what element it is. So hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, beryllium has 4 protons, and so on and so forth. Now, there are 118 different elements that we have discovered so far, and there could be more. We just don't know of it yet because the ones that we have discovered, particularly the later ones, only exist for very short amounts of time. However, there are theories that it will exceed 118, and potentially there are islands of stability, to use quote marks. And these islands of stability are where it doesn't decay almost instantaneously. And I think it's a very interesting topic, so if you want to kind of get some background reading done, I would recommend doing that and reading about that. Now, it's important to note that elements can be represented with symbols, and this is particularly important for when we're talking about equations. So the symbols are usually 1 to 3 letters long. I mean, all the ones at the minute are 2 letters, but back when there were placeholder names like ununtrium and ununhexium and whatever those names were, they had 3 letters. It was like UUT or UUU or whatever. So they're generally between 1 and 3 letters, but most will be between 1 and 2. Now, isotopes are a variation of an element. So it's the same element, same protons, but you've got different amounts of neutrons. And this affects the properties, so often isotopes will have very different properties. For example, carbon-12, we have a lot of carbon in our bodies, that's why we're carbon-based life forms. But, you know, you've got the properties that make coal, graphene, diamonds, things like that. But you've also got things like carbon-14, which is radioactive. Now, carbon-12 isn't radioactive, but carbon-14 is. And so you can see kind of how isotopes affect the properties. And because of all these isotopes, you've got something called a relative atomic mass. So you've got the atomic mass, and that's all fine. But what if you've got... So, for example, if you were to look on a periodic table, you'd see that chlorine's atomic mass is 35.5. How can you have half a mass if atoms are as small as it goes, really? So, you have something... But the reason for that is because there are many different isotopes of chlorine. You've got chlorine-35 and you've got chlorine-37. And they're in such a ratio that using the equation down here, which I'll explain in a minute, you actually get an answer of 35.5, which is why often you'll see copper as well having not a whole number for its atomic mass. Now, if you use the equation down here, this basically means you do the atomic mass of isotope 1. So, say we were to use chlorine as an example, you do 35 times the percentage. So you do 35 times 25, because it appears in 25% proportion. I've done that the wrong way around, sorry. It appears in 75% proportion, so you would do 75 here instead of P1. And then you add that to I2, so that would be the 37, chlorine-37, which is, so 37 there, times 25, and you'd add those two together, and then you'd put them over, or divide that answer by, your percentage 1, so 75, and your percentage 2, which is 25. And if you do that correctly, then you should end up with an answer of 35.5. Which makes sense because there's more of 35 than 75, so the atomic number will be closer to 35. And this brings us on to our next point. So we're going to talk about compounds now. Compounds are 2 or more elements chemically bonded together, and this is due to the movement of electrons. So every atom wants a complete outer shell, just like this one. However, not every atom has it. For example, lithium would have these 2 in here, and just 1 in this next shell. But it wants a complete outer shell. So it can either do that by gaining 7 more electrons to look like this, or losing 1, and so you just take out the whole outer shell there and leave it just with the shell with 2 in. But all atoms want this, so you can get ionic bonding, which is where electrons will be given or taken away from atoms and given/taken away to others, and then the difference in charge, because giving electrons to something will change your charge and their charge. Yours will become positive and theirs will become negative, because you got more protons than electrons then, or less in the other person. And so the opposite charges attract and they bond together. And there's also two other types of bonding: covalent bonding, which is where electrons are shared, and metallic bonding, which is where electrons are shared, but in a slightly different configuration again. But I'll talk about those in another video. Compounds have different properties to the elements. So often you'll find that sodium is a soft metal. It would set on fire in water, but when you bond it with chlorine, which is poisonous in gas form and is a gas, it becomes sodium chloride, which is more commonly known as salt. And this salt is soluble in water, and it doesn't set on fire, thank goodness. And it's not poisonous. Well, so long as you eat it in moderation. So often you'll find that the properties are quite different in the compounds. And compounds have formulas, so these build on the symbols. So often there are lots of elements out there which have a chemical symbol that is maybe the first two letters of their name or the first letter, such as carbon or oxygen, where they're just C and O. Or you might have something like sodium, which is Na, like up here. Now, this might not be obvious, but it actually is often derived from the Latin. So lead is Pb, and the reason for that is it's plumbum in Latin, which is where we get our word for plumbing from, which is a different topic entirely. But I always think that's quite interesting to know. But it's important that you remember some of these because you may need to represent the elements in the equations that you're doing. So these are very common things, symbols for compounds. This is carbon dioxide, and little numbers represent how many individual atoms of the element there are. So there's 1 carbon, 2 oxygen, and you've got ammonia, water, and this is glucose here, which is important for biology. And now we'll go on to chemical equations. So you can write it as a word equation. So you can do oxygen plus glucose is water plus carbon dioxide, which I'm sure if you know biology, you will know as the equation for respiration. And these are good because all you need to know is just the name of the stuff that you're bonding together and the products that you're forming. But it doesn't really tell you much about the equation. So often we use symbol equations. So this is the symbol equation for the unbalanced symbol equation for respiration. So O2 plus C6H12O6 plus goes to H2O plus CO2. But it's important that you balance symbol equations. So this isn't balanced. So I would get maybe 1 mark or 2 marks in the exam for doing this. But I've got, I won't get full marks because it's not balanced. So there's one method that I really like using to balance equations, and that is you literally just say how many atoms of this element have I got on here. So we've got oxygen, we've got carbon, and we've got hydrogen. So just write them in the middle there. I'm actually going to move my pad so that it's more central. I'm just focusing here. So on this side, you've got 3 oxygens, you've got 1 carbon, and you've got 2 hydrogens. And on this side, you've got 8 oxygens, you've got 12 hydrogens, and you've got 6 carbons. So, and you want to match this out. So, if you put a 6 in front of this, then that means you've got 6 lots of carbon dioxide. So then you would have 6 carbons, and now you would have another 12 on top of that 1. So you'd actually have 13. But then this still isn't fully balanced. So the next one that I'd say that you'd go for is you try and balance this H2O here with this one, because your oxygen is close, but this isn't even yet, so you need to get another one of those. So if you were to put a 6 in front of this, you'd have 10 more hydrogen molecules, so 12 in total, and you'd actually have another 5, on top of this, which takes it to 18. So then you just need another 10 here, so you'd put a 6 in front of this, so you've got 12 over here on top of the 6 here. So then you've got 18. So the balanced product is 6O2 plus C6H12O6 plus 6H2O plus 6CO2, and that is fully balanced. So that's all about atomic structure. I hope you found it useful. If you need more help in balancing equations, just leave a comment below, because I know that is something that people struggle on, and I would be very happy to do a dedicated video on that, just going through some practice questions. So there will be more on the way either later today or tomorrow, more about atomic structure and the periodic table. And with that, good night and God bless.